So good morning all. So today we are going to discuss about the pulse code modulation, and it is a part of a digital modulation scheme through which we can convert the analog signal into a digital signal, and the digital signals are basically the binary data. So what are the basic block diagrams, or what are the basic steps behind this PCM that we are going to discuss today? Uh, so so today we are going to discuss first one is our basic idea behind the PCM. Then what are the basic steps? Basic steps such as sampling, that is quantization, encoding, and how we are going to decode the received signal after the transmission of the PCM signal. So that we are going to discuss today, as well as the logic behind to implement the PCM, as well as the program to implement the generation and detection of a PCM signal. And we are going to execute all these things with the help of a MATLAB tool. Okay, so as we know that these are the basic introduction of an PCM. As you can see, the analog voice must be translated into a series of binary data before they are transmitted. So basically what it indicates that when we are going to transmit our signal, that is voice signal or a message signal, so it is analogous in nature. So when we are going to transmit the analog signal with the help of a digital device, we need to convert into a digital value. Then only it will understand or it will respond to the given sequence. So how it will respond? First we need to convert the analog signal into a digital values. So digital values uh, are identified with the help of binary data. So our main motive is to convert the analog signal into the binary data. So analog signal, how we are going to convert into binary data? First it need to be sampled, second it need to be quantized, and third it need to be encoded. So representation of these all the three particular steps in a particular platform, we can generate the digital value. So with the help of this PCM, the amplitude of the sound wave is sampled. That means what I told, that analog signal is sampled at a regular interval of time, and that sampled signal is identified with the help of a sampling frequency which is satisfying the Nyquist rate. Okay, and the Nyquist rate states that the sampling frequency must be greater than equals to twice of the analog input frequency. So if my analog signal is having 5 kilohertz, that means the sampling frequency must be of 10 kilohertz, twice of that, or more than 10 kilohertz. Then only it will sample at a regular interval, and the intersymbol interference will reduce. Quite aware of it, that how to reduce that ISI. Okay, next, the difference between the original analog signal and the translated digital signal is called quantization error. So this error also we come into know discussing about the digital modulation scheme, that how an error will come into picture. So basically it will compare the result what we are transmitting, what we have received. If it is original analog signal and the translated digital signal, if I will compare, some steps will vary. So that steps indicates that it is a error is identified. So that is called as a quantizing error. So that quantization error we are not going to discuss in more deep, rather than we are discussing about the generation of PCM signal and detection of PCM signal. So here you can see it is a basic block diagram for a PCM signal or PCM encoder. This PCM encoder is also called as AD converter. Okay, it will convert the analog signal into digital data. So as you can see, left hand side, the analog signal generator is there. It will generate the analog signal. So analog signal is first it is enters to the sampler, then it is quantizer, then it enters to the encoding. So sampler means it will sample the whole signal into regular interval of samples. Okay, and you can see down it is called as a PAM. So it is a pulse amplitude modulated signal, also we can see the sample signal. Now once this pulse is identified, we need to quantize the sample. So when we are quantizing, means we are compacting the time period and identifying only the discrete value. So remember that the sampling and quantizing steps is, if I will combine, it will called as a discretization. Have told that sampling and quantizing, these are the two steps through which we can generate the discrete signal. Now once this discrete signal is generated, the encoder step is the encoder. So the discrete level will be assigned with some binary data. We have some relation that if the quantization level is n, then L is equals to 2 to the power n, where n is the number of binary bits. So if the number of level is 8, each level is represented with 3 binary bits. So that is called encoding process. And at the end, the whole analog signal is represented with a digital data. So as you can see that analog signal is converted into the digital data. So this is called as a PCM, PCM pulse code encoder or pulse code modulation. This is our encoder. Modulation, why it is called modulation? Because the characteristics of analog signal is going to change with respect to the pulses, and the pulse are going to be represented with the binary data. Okay, so next we can see so next is the what is the sampling. So as I have told, analog signal is sampled at a sampling time period Ts. So what is Ts? Ts is equals to 1 by Fs. What is Fs? Fs is the sampling frequency which satisfies the Nyquist criteria. Okay, so Fs is equals to twice of greater than equals to twice of Fm. Fm is the modulating frequency which is provided to the AD converter, or you can see it is called PCM. Okay, so there are basically three sampling methods are available. One is ideal, one is natural, and one is flat top sample signal. So ideal is the impulse at which the sampling instant. Natural is the pulse of a short width with varying amplitude, and flat top means the flat of the top of the sample is represented with a flat value. So here that ideal sample is just as a impulse function. Okay, only the discrete value is available at the instant of time period Ts. At a regular interval of time period Ts, the signals are available. Okay, and next one is natural sampling, means the samples are available. It is naturally, amplitude variation will be there. But in flat top, you can see amplitude are at a constant, means the top of the pulse is as a flat only. It is not varied with respect to the analog signal. If it is varied with respect to analog signal, then we can say it is called natural sampling. So these are the basic type of sampling which is available through which we can generate our discrete signal. So if we are going for the ideal sample, this one, no need to convert, it is already in a discrete position. But if we prefer for natural or flat top sample, then we need to quantize it, and the quantized signal are assigned with the binary data through which we can generate the digital information or the pulse code modulated signal. Okay, so here you can see the quantization process. So second step is the quantization process. In this, the sampling result is a series of a pulse varying with the amplitude and the ranging with a minimum with respect to a maximum. So a max and a minimum is the maximum amplitude available in the modulating signal. It will fix that limit. Then the amplitude values infinite between the two limits. The amplitude will vary with respect to the two limits. Okay, a max and a min. Within that limit, we have to divide into L number of zones. Okay, and that L is called as a number of levels. So L is equals to 2 to the power n, and the space between the two consecutive levels is called as del. Okay, so that is called step size. So del is equals to maximum minus minimum divided by L. L is equals to 2 to the power n. Okay, so this del is indicates that it is a step size. So this step size will vary, will remain constant throughout the system, and if there are 8 levels are there, between each and every levels the step size is del. Depend upon this del, your quantization process will identify whether it is a uniform quantization or whether it is a non-uniform quantization, because there are two type of quantizations are available. One is uniform and one is non-uniform. Uniform means if the step size remain constant throughout the system, if the del remain constant, and non-uniform means if the del value changes with respect to your input message component, then we can say it is called non-uniform uh, quantization process. So this is the basic gist of a quantization. And quantization levels, if there are 8 levels are there, that means it will vary from 0 to 7, that we will see. And the midpoint is called as a value of that midpoint is identified as a zone. Whether it can see the quantization zones are identified. So first we have to identify the Vmax and Vmin. Let us consider the Vmax is 20 and Vmin is minus 20. And the number of levels I'm going to identify as 8. So L is equals to 8. So how many number of binary bits are going to assign with respect to the levels? It is 2 to the power n. So 2 to the power 3. So 3 number of binary data is to be assigned with these levels from 0 to 7, because if there are 8 levels are there, that means it will be assigned from 0 to 7. And what will be the zone width, the space between two levels? As we in the previous slide we have seen, del is equals to Vmax minus Vmin divided by L. So Vmax is 20, Vmin is minus 20, so minus minus will be plus. 40 divided by 8, L is equals to 8. So the step size is 5. If the step size 5 remain constant throughout the system, then we can say the quantization process is a uniform quantization. Okay, but if the del remain, if it is changed with respect to the input signal, then we can't say it is uniform. We will say it is called non-uniform quantization process. Now the 8th zone, how we are going to assign? First, as we can say that step size is del is 5. So that means from minus 20 to plus 20, if I'm going to identify how many number of levels are there, ranges will be identified. So first, minus 20 to plus minus 15, minus 15 to minus 10, minus 10 to minus 5, minus 5 to 0, 0 to 5, 5 to 10, 10 to 15, 15 to 20. As you can see, the distance between, or the space between minus 20 and 15 is 5. Similarly, 15 to 20 is also 5. So that means these levels are equispaced at a distance at a step size of del, which is equals to 5. Okay. And what are the midpoints? We have to identify these midpoints, because these midpoints are going to be assigned with a binary value. So the minus 20 to minus 15, the midpoint is minus 17.5. Okay. Minus 15 to minus 10, midpoint is minus 12.5. Then minus 10 to minus 5, midpoint is minus 2.5. Similarly, 5 to 10, like this, the midpoint you have to identify. So these are the midpoints through which we will assign the binary values. Okay. So next you can see encoding. So encoding is a process through which in that zone how we are going to assign the binary data. So each zone is assigned with a binary code. So what is the code length? 3, because L is equals to 8 means the code length will be 3, 2 to the power n, 2 to the power 3. So the number of bits is required to encode the zone, or the number of bit per sample, as it commonly referred to as obtained as a, what I have told, n is equals to log base 2 of L. So L is equals to 2 to the power n. So n is the number of bits. If the number of level is 8, how many number of bits we are going to assign? 3 bits. So n is equals to 3. So for 8 zone, we are going to assign the 8 combination of 3 bits. 000, 001, 010, 011, 100, 101, 110 and 111. So these are the combination of 3 binary data for 8 levels. Now we are going to assign all these things. How we are going to assign? First, 00 is assigned with the lower one, means minus 20 to minus 15. So midpoint we are going to assign as 000. Similarly, minus 15 to minus 10 we are going to assign 001. Similarly, next one is 010 is assigned with minus 10 to minus 5. Then 011 is assigned with minus 5 to 0, then 0 to 5, then 5 to 10, then 10 to 15, 15 to 20. So like that we will assign the codes. Okay. Now here you can see it represent the clear picture how we are going to assign the binary levels. Left hand side you can see there are 8 levels are identified. 0 to 7 means there are 8 levels are there. Okay. And here minus 4d to plus 4d, because there are 8 levels are there, and these divisions are identified 4d. Now this 0, this is 5, this is 10, 15 and this is 20. So midpoints were identified, and these midpoints are assigned with the binary data. We need to code it because these are the discrete value. Discrete value are assigned with the binary data. It is called as encoding process. Okay. So here you can see normalized quantized value is identified first. So first of all, the normalized PAM signals are all we are going to identify the normalized PAM values. Okay. Now normalized PAM values are represented with the normalized quantized value. So normalized quantized value means it is the nearest value. If it is 1.22, the nearest value is minus 1.5. If it is 1.50, 1.50, fine. If it is 3.25, near about it is 3.50. If it is 3.94, near about it is 3.50. So 2.20, 2.50. So these are the nearest value. Okay. So this nearest value, when we are going to identify the error, this is the normalized value and this is the normalized PAM value. So if you take a difference between these two, you will get a normalized error. So this is called as a normalized error. So normalized error are identified with the quantization code. Done. So these quantization codes are represented with minus 0.38 is assigned with quantization code 2, 0 is assigned with 5, plus 0.26 is assigned with 7, minus 0.44 is assigned with 7, zero point 0.3 is assigned with 6, then 0.40 is assigned with 2, then minus 0.24 is assigned with 1. All these things are assigned with respect to these particular positions. Okay, remember that these particular positions. So here it is 2 means it is 0, 1, 0. So these are the quantization codes. These quantization codes are represented with binary data. So that means the codes are represented with binary data means it is a pulse code generation. So pulse are coded with some binary data. Okay. So this is called encoded words and these encoded words are going to be transmitted. So this is called PCM generation. Okay. So next you can see this is coder. So here what happens, we receive the binary data. We need to extract the analog signal. So what will happen? We have the PCM decoder in which we have to make some connect with respect to the samples and then we are going to pass through a low pass filter. Basically when we are receiving the binary data, it passes through a holding circuit. Holding circuit is followed by a filter which will reconstruct to the original message signal. So here to recover the analog signal from a digital signal, we have two steps as I have told. First, it will pass through a holding circuit. Okay, the until it will hold the potential until the next pulse arrives. That is the first step. Second, we need to pass that output of the holding circuit through a filter. Okay, which will reconstruct the original signal. And this higher the value of L, the less distortion signals are identified, because if the number of levels are increased, the quantization error is decreasing. Okay, if the quantization error decreases, that means the error effect is less. If the quantization level increases, effect of quantization will be very less. Okay, so and the signal recover reconstruction will be very easy if the number of levels are high. Okay, so this is called as a PCM decoder. Now this is the basic implementation of PCM signal. As you can see, there are three blocks I have written and I have divided into three particular parts. First, we need to generate the signal. Then the quantization process is there. This is the basic steps behind to generate the PCM signal. First, we will understand that. Then we will go for the generation and then we will go for the detection. Okay. So first here you can see I have written CLC clear all. These are the basic commands for our program. First we have to identify the time period, because here we are giving the input signal as the analog component, which is a time dependent one, and we need to define the time period. So here I have defined 0 to 20 is the total time period and it was divided with a time period of 0.0005. So this is the range in which the total time period is going to be divided. You can put 0.5, you can put 0.25, it depends on you. Okay, then partition was done from -1 to 1. This is the total length is identified and this partition is done at a range of 0.1. Okay, then there is a code book because we need to code the data. So here we require a defined function called code book. So code book is having a length is states as a partition value minus 1 to 1.1, and it will vary with respect to zero point 0.1. So this is the code book. So with the help of this code book, we will assign the binary values. Okay, and x is equals to sine t. So we are using the analog signal as a sine t. Okay, next we need to quantize this signal. So in MATLAB we have a syntax called quantize. So if we give the command as quantized x comma partition comma code book, it will quantize the signal. Means output will be the discrete signal. Okay. So index comma quants is equals to quantize x comma partition comma code book. So this is the command through which we are going to quantize this signal. Okay. Then we have to plot it. As we know that we need to plot the signal. First we will plot the sinusoid signal, then we will plot the quantized signal, then we will plot the PCM signal and encoded values. Okay, so first subplot 3 comma 1 comma 1, plot the t comma x value, that means sine signal will be plotted, title it, that is called message signal, then x level is the time period, y level is the amplitude, then subplot 3 comma 1 comma 2 means the second position, in which we are going to plot the quantized signal. So quantized with respect to whom? Quantized with respect to the time period t. Okay, so here quants t comma quants, and this figure will reflect the quantized signal and the time period. This is one method. One more method is that how to generate the quantized signal. The simple step is that if you identify x is equals to sine t, then you put stem of x. If you provide the stem of x, means the whole signal, the whole analog signal is going to be represented in a discrete manner. If the discrete manner is identified, that means it is a you can say it is called quantized signal. But since the quantization process we are discussing, that means the quantization we need to represent, we need to identify that quant value. Okay, so that it will be easy to understand. So this quantized, after this quantization we have the encoding. Okay, once it is encoded, once it is means quantized, next one is what we need to assign the binary data to those quantized level. So y is equals to u encode quant comma 3. So u encode quant comma 3 means that quantization levels will be assigned with the binary data 3 terms, or this is third position you can identify, that is it is a command called encode it. Those discrete value are going to be encoded, going to be represented with binary data. Okay, and we need to plot it 3 comma 1 comma 3, you can give the subplot value, then plot the signal, that is that signal y, and that signal is called as a PCM signal. And once this PCM signal is done, that means we have converted the analog signal into the PCM signal. So once this PCM signal is understood, then we can go for the generation and the detection. Okay, I will execute this program for you so that you people can understand that what are the lacuna behind it. If any thing need to be changed, what are the figures are identified, what sort of figures will come, and how we are going to analyze it. Okay, so let me minimize it first. One minute. This is the I'm minimizing. So this is already I have opened in our MATLAB editor window, in which I have written the code. First is our CLC, then CLR, clear all, then time we have identified, then partition we have given, then code book is given, x is equals to sine t. So this is the first part to generate the message signal. So up to this is called as a representation of message signal. Okay, next you need to quantize this signal. So when you are going to quantize, you have to define that index comma quants is equals to quantize x partition comma code book. So this is the command through which we can quantize the input signal. Input signal means this sine signal. Okay, you need to plot it. So subplot it, then plot t comma x, title message signal, x level as a time period, y level as a amplitude level, then subplot the quantized signal, that is plot t comma quant. It is a quantized value will come into picture. Then you need to represent with the coded value. Okay, that is called you encode quant comma 3, and you have to plot this signal. So if you are writing all these commands, it is quite easy to understand that how we are going to represent the analog signal into the PCM signal. The PCM signals are represented in a step size because uniform quantization will be there. So uniform quantization means your step size will remain constant. As I have told, so first you need to generate the signal, that is x of sine t. Then you have to quantize the signal. Then we have to assign with respect to the figures. So when we are identifying the figures, we need to subplot it. We need to plot the signal. First we are going to plot the message signal. Then we are going to plot the quantized signal, and then we are going to plot the PCM signal. So PCM signal is represented with some step size, so that we will see, and then we will compare the PCM signal with the quantized, so that quantization error will be identified from that figure. So this is the basic steps behind to generate the PCM signal. So I have written all this thing. So after writing all this code, you need to save it. A path will be identified. uh, Identify the paths, save in a particular folder, and then you go for the run option. So here change folder it was asked, so I have changed it. Then it is running out, and you can see this is the figures will be generated. So first figure is our message signal, so it is a sinusoidal signal. Okay, you can see that sinusoid signal, and the time period is what, 0 to 20 we have identified. Okay, so that means 0 to 20 is the time period within which the sinusoidal signal is going to be represented. Next you can see this is the quantized signal done. So this quantization is done with respect to the uniform quantization. This is the uniform quantization you can see here. Then after the uniform quantization, you need to assign with the binary data. So binary data is represented with the pulses. So pulses, here you can see the pulse amplitude is 4, then it is 5, then it is 6. The step size remain constant. Here the amplitude remain constant. Here it is amplitude is high. So here amplitude is high. Now if I will take this particular PCM signal, okay, this PCM signal is represented with the binary data. So this is the basic waveform. So this PCM is represented with the binary data, and binary data is going to be transmitted, and those binary data will be represented in different sort of manner. Either it is in we can go for line coding. Okay, either it is in terms of uh, uh, non-polar, either it is in a form of polar, return to Z, non-return to Z, or it is in a form of a Manchester, or in bipolar or AMI, whatever it is. So it is a basic representation of a quantized signal and PCM signal. Okay, so I'm closing it. So this is the basic steps through which we can understand the generation of PCM signal. Next we will see that how this PCM signal is generated. The same thing we are going to discuss once again, and how it is going to be detected. And in that we are very deeply we are going how that quantization helps, how the del value remain constant, what are the minimum value are identified. Okay, so that we will discuss. So this is the PCM signal we have generated. Next, we are going to discuss the generation and detection of PCM signal. So first, as I have told, here the logic is according to the discussion what I have made in the previous slide, that first we have to identify the number of binary bits. These binary bits are going to be identified with respect to the number of levels. These levels are called as quantization levels. These quantization levels space size we have to identify. Distance between two quantized levels, that is del. So del is V max minus V min divided by L we have to do. So all those things we are going to incorporate with the help of this programming language, and then we can easily recover the original signal with respect to the transmitted and with respect to the encoded data. Okay, so step by step we will see. So here, first, the initialization process. For any signal to generate, we need to initialize it. So first is CLC, close all, clear all, that all things are available. That then n is equals to input, enter your PCM, whether it is a n bit PCM. N is equals to 4, you can provide. N is equals to 8, you can provide. If it is n is equals to 4, that means 2 to the power 4. If n is equals to 8, that means 2 to the power 8 it will come. Okay, number of levels will increase. If the number of value of n, if you give 2, that means n is equals to enter the n bit PCM. Okay, after that n1 is equals to enter the number of sample period. Means sampling period you have to enter the number of samples in a period. Then you have to define L. L is equals to 2 to the power n. The number of levels are identified. So this is the initialization. Next, we have to generate the signal, analog signal. Once the analog signal is generated, then we can go for the quantization process. So x is equals to 0 to pi by n1 is to 4 pi. That is 2 clock cycle I have considered, 0 to 4 pi. So 0 to 2 pi divided by n1. N1 is the number of samples will be divided. Okay, so that I have represented. N1 is the number of sample have to be selected. Then you have to define the signal. So here we are going to use the sine signal with an amplitude of 8. So here you can see S is equals to 8 sine x. Then you have to plot it. Subplot 3 comma 1 comma 1, then plot S. S is the sinusoidal signal, it will come. Then you can title it, it is an analog signal. Y-axis and y-axis and x-axis, you can assign amplitude and time period. Then some plot 3 comma 1 comma 2, that means quantized value you have to represent. So what you have to do here, quantization is done with respect to stem command, as I have told. If you write stem of S, it will identify the instantaneous quantized signal. Okay, instantaneous quantized signal, that is called sample signal. So you can write it is called sample signal, and assign with y level as amplitude and x level as time period. Okay, so this is the generation of a sample signal. Sample is done with respect to the stem. Okay, so that is called discretization also. Next, quantization process. So in quantization process, what you have to see? First, we have to identify the Vmax. Second, we have to identify the Vmin. Then we have to identify the del. And then we have to identify the part, how it is going to vary, and how we are going to assign the values. So when we are going to assign the coded values, we require for loops, okay, for different positions. So first, in the left hand side, you can see Vmax is equals to 8. Yes. Then Vmin is equals to y minus Vmax. Yes. Then del is equals to Vmax minus Vmin divided by L. So that is the given formula what we have for the step size. Then part is equals to what? How many times it will vary? Vmin is to del is to Vmax. So this is the level between Vmax and Vmin. Okay. Next, you have to identify the codes. So code is assigned where? In the half of the midpoint. So del by 2. So del by 2, del Vmax plus del by 2. So this is the code. Okay. Then it contains the quantized value. Then again the quantized signal you have to identify what we have written in the previous one. I index, quant and quantize s comma part comma code. So here also same thing. Ind q, then it is a quantized s part and code value. So code here we have given Vmin minus V del by 2, then del, then Vmax plus del by 2. Okay, then length you have to identify because the number of iterations we have to see. So length means length of the index value. L2 is the length of quantized value. So number of quantized levels are identified. According to that, for loop will continue and assign the binary data. So here it is for I 1 is to L1 is the first. Then if IND of I is 0, that means we have to see whether the binary bit is assigned to the started value from 0 to n or not. Okay, if the index value of I in IND of I minus 1 end it, and I is equals to I plus 1. Similarly, for next one, I is equals to second length with respect to the quantized level Q. So I is equals to 1 is to L2. Then for I is equals to 1 is to L2. Then if Q of I, you have to check that whether it is a midpoint or whether it is a del is satisfied or not. So V min minus del by 2 to make the quantized value levels. So Q of I is equals to V min plus del by 2. So this you have to identify. So midpoint we have to see. You have to end this loop, subplot the value, you will get your quantized signal. So stem of Q, you will get your quantized value. Grid on, display the quantized value, title it, then label it with respect to X label or with respect to Y label. If Y label is amplitude, X label is time period. Next, once the quantization is done, next you have to encode it. So how we are going to encode? We are going to encode what it is. Decimal value, which is the discrete value, need to be converted into binary. So we are going to, so in this encoding process, you are going to kind of represent the discrete value into a binary data. So what we are going to do, we have to assign the decimal value to the binary data. So we are going to use the code called decimal to binary. So that is DE to BI. So always remember that when we are encoding, decimal to binary we are doing, and when we are decoding, then binary to decimal we have to write. Okay. So it is decimal to binary index value left MSB. From left hand side we are going to identify and convert the decimal to binary value. K is equals to 1, it is a value we are going to assign first. Then for I is equals to 1 is to L1. Then for J is equals to 1 is to N, and we have to code it. So number of levels are identified, number of binary bits are going to be represented with N value, and number of levels are there. L1 is the number of length. Okay, and in that length how many number of binary bit we are going to assign. So that is called as a code. So that coded of K is equals to code of I comma J. So it will identify both the position and it will assign the code value, and the row factor will increase. J is equals to, you have to increase the loop with J is equals to J plus 1 and K is equals to K plus 1, end it, and I is equals to I plus 1. It is need to increase the positions. It will change the position. Number of iterations are there, and it will continue up to how much? L1 and N value. Okay. Now once it is done, a sign is done, you need to plot it. So plot 2 comma 1 comma 1 grid on. Then staircase, because here the quantization levels are identified in a stair, you have to code it and display the encoded value, encoded signal. You have to make the axis, define the axis. You can put the axis command, it's fine if it is not there. Okay, then title it encoded signal. Y level is amplitude, X level is uh, time period. So once this is done, then you can go for the demodulation of PCM. So demodulation means you have to reconstruct the binary data into a analog signal. So here I have written quant is equals to reshape the coded signal into the binary into the analog signal. So coded, reshape of coded comma n comma length of code divided by n. Index, here what happens, we are receiving the binary data, we need to convert into the decimal. So binary to decimal, quant left MSB. Then Q is equals to same del operator we are going to use because we need to synchronize it. Okay, so del into index plus V min plus del by 2, get the actual quantized level, subplot it, and whatever the signal we are going to get, it is called demodulated signal or the recovered signal. Okay, PCM decoded signal. First we have seen generation, then quantization, then encoding, then demodulation is called as a decoding of a PCM signal. So when I'm going to execute, 1 minute. So I have written the program with the same command what I have discussed now. First, you need to generate the signal. Signal generation is done up to grid on over. After the signal generation, you need to quantize it. So how we will quantize? Sampling process is there. So sampling is done, identifying the subplot and the plot with respect to the stem and Y level and X level up to this much. It is a sampling process. Sampling means you need to sample the signal at a regular interval of time. Once the sampling is done, next step is quantization level. So in quantization, what we are going to identify? We are going to identify the step size first. So step size identified how? how we can identify the step size del? First we have to identify Vmax, then Vmin, then del, and then midpoint we have to identify. Then you have to code it. Okay, which particular position you are going to code. So it is a Vmin minus del by 2 is to del is to Vmax del by 2. So this is the range within which we are going to code it. Then you have to int comma q quantize this signal. Then identify the length of the indexed value and the length of the queue. Okay, quantization. Then according to those particular position, you need to assign the values one by one. So this is the assigned values. Okay, identification of the mid values, and you have to generate the quantized signal. So once this quantized signal is done, then you can go for the encoding process. So this is the encoding process, means we need to is assigned, then you have to convert the decimal value into the binary. That means we are encoding the data. Okay, encoding what? Encoding the binary data. Resultant will be the binary, because decimal value is the discrete positions value we are going to convert into the digital data. So digital values are identified and we need to plot it. So that plot is called as a encoded signal. Y level and X level both are identified. So here it is, X level is amplitude, and X level I can write X level as a time period. Okay, so it is time. I will close it. Okay, so this is the time. Then next is the demodulation of a PCM signal. So in demodulation, what happens? We are receiving the binary data. We need to convert into a decimal value. So it is a binary to decimal is written here. So binary to decimal quant left MSB. Then what is Q? You need to synchronize the position. So here Q is equals to del into index plus Vmin plus del by 2. So it is a quantized value we can get back, and we have to plot it, and this resultant is called as a demodulated signal and X level. Okay, so after writing all this code, you need to save it, and once it is saved, go for run. So here it will ask what is the n value of n bit PCM. If the number of bits are more, that means error will be less. Remember that, because number of levels are going to increase. So in order to minimize the quantization error, your number of levels must be high. So here I am using n is equals to 8. Okay, and enter the number of sample for in a period. So it can be 10. More identify the positions. So let it be 10. So if I am giving this particular value, my resultant waves will look like this. So first figure is, you can see here, first is our analog signal. So this is the sinusoid signals are identified. Then after generation of sinusoid signal, the sample signal is generated. So these sample signals are identified. It is an instantaneous value. We have written stem of S. So sample signals are identified. Now once the sample signals are identified, next we went for the quantized signals, writing that code book, code and quantized and all. So you can see that quantized and the sample signal both are same. Why? Because the sample signal is the fixed value. Okay, positions are fixed. Here sample, it is called the instantaneous sample we have used. So instantaneous sample, if you are giving output of an instantaneous sample to the quantizer, then resultant will also become the same, because it is need not to quantize any sort of time period. It is already, it was quantized. So if you give the natural sampling or flat top sampling, then the quantized levels will be identified as a discrete value, and the sample signal will be identified with the natural or flat top signal. Okay, so this is about the instantaneous value. Okay, like this the sampled and quantized signals will be identified. Now once it is quantized signals is done, then you can see that here in the second figure it was encoded. So here the binary data is available, you can see. So these all are binary data, 1010 and 01. All this binary data is available. So this is called as an encoded signal. Now this encoded signal can be represented in a different format. Either you can represent in Manchester, either you can represent it in AMI, either you can represent it in NRZ, return to Z, in different sort of manner we can form. Once this encoded is done, that means the decimal is converted into binary. Next is we need to recover the original signal. So for recover of original signal, what we do? We are receiving the binary data, we need to convert into decimal. So binary to decimal command is used, and then we can reconstruct with the help of a del operator. We need to synchronize that. Once it is synchronized, you can see that the modulating signal, which is a sinusoid signal, is quite similar to the demodulated signal. So this is called as our decoded encoded signal as well as demodulated signal. So these are the basic steps behind which you can understand the generation of PCM signal and the detection of PCM signal. So with the help of this, we can analyze the working principle of PCM, what are the basic components are available, what are the steps are available, how execute this code with a given value. You can change this value, and according to that, figures will come into picture. This is the encoded, this is the demodulated one, and the first figure will show the analog input, and then sample signal and quantized signal. So you can see that this analog signal and the demodulated signal are quite similar. So it is a generation of a transmitted generation of original signal with the help of PCM encoder and decoder. So these are the basic steps. Go through it. These slides also, it is available in this video. Go through it, identify these codes, execute it. It will help you to understand the working principle of PCM, how it is generated and how it is demodulated. Okay, and with the help of this slide, you can make a note of it, because depend upon this, the YY is going to be asked small programs we are going to ask, because since it is an online, so we will see how it is going to be executed in a very well manner, and depend upon this PCM and all. So try to execute this QPSK transmitter also we have discussed, PCM signal we have discussed, as well as the representation of NRZ and RZ components are represented. So if time permits, I will go through the eye diagram also, and I'll prepare one more video for that. Till then, you try to practice all these things, and even you can practice online by using the online MATLAB tool. But the in online certain codes are not available, like quantized and all, that is comes under the communication toolbox. But in online, which is a free source, may not they provide that particular facility, but try to execute in the installed software only. Okay, so till then, I will wind up this session, and if any doubt is there, just call me and we will discuss in the very brief manner. Okay, till then, thank you all.